friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 4. This is lecture number 3 and we will continue with the estimation of runoff, and today we will take up a rational method, a very popular method of estimating runoff. So, as already mentioned, the only topic we will cover today is peak rate of runoff by a rational method. So, rational method, it is one of the most popular method of estimating peak runoff rate for designing soil conservation structure. So, of course, we have already discussed runoff, and we know that while designing any kind of soil conservation structures, be it discharge structures or detention structure, we definitely require the runoff volume, and of course, this method gives us peak runoff rate. So, it is more important for any kind of a conservation structure. And peak runoff rate is expressed in this method by this relationship QP equals to CIA, equation number 9. Remember, we are continuing with the equation number for the entire estimation of peak runoff rate. So, that is why this is equation number 9, because we have used other numbers in previous lecture. And here QP is the peak runoff rate in cubic meter per second, C is runoff coefficient, I is rainfall intensity in meter per second for a duration equal to the time of concentration of the watershed and for a desired return period. So, that is very important. The intensity definition is very specific and it has to be always kept in mind while using the rational method, that this rainfall intensity should have a duration equal to the time of concentration of the watershed. So, that is a important condition, and of course, for the desired frequency or desired return period, which we discussed that depending on the life of the structure, we decide what frequency we have to use or what probability we have to use. In order to remember, we discussed the probability or return period. So, what return period we will use, that decision has to be made, of course. And A is the area of watershed in square meter. So, here it is written in plain form CIA. So, I is in meter per second, area is in square meter. So, that is why we get QP equals to cubic meter per second. In some of the textbooks, you will find this relationship in this form. CIA equals to QP equals to CIA by 36, but the units there are centimeter per hour and area is in hectares. So, obviously, you have to remember the units also for using this relationship. So, in order to avoid that complication, we can simply use this relationship, that is I is in meter per second and A is in meter square. So, that is why we get discharge in cubic meter per second. That is a typical unit discharge unit we use, that is cubic meter per second, or we said it is cubic. The method, of course, has certain assumptions which we will see little later. So, its applicability limited to watersheds having area less than 1300 hectares. Of course, this number is also not a very fixed number. In different literatures, you will come across different numbers. The idea is that the watershed, because there are certain assumptions, so the water should be of reasonable size in order to be able to use this method. And there are two significant assumptions on which the rational formula or rational method is based, that is, rainfall occurs at uniform intensity for a duration at least equal to the time of concentration. So, that is why while defining intensity, we say that intensity should have a duration at least equal to the time of concentration, and this assumption says that rainfall occurs at uniform intensity for a duration at least equal to time of concentration. That means, whatever be the time of concentration of the watershed, for that duration the intensity of rainfall remains constant, whatever value we take, that remains constant. The other assumption is that rainfall occurs at a uniform intensity over the entire area of the watershed. So, the rainfall is this one is about time, one is about areal distribution of rainfall. The second was saying that rainfall is uniformly distributed over the entire area of the watershed. That means, the entire watershed area contributes to the runoff because of this rainfall intensity, which has a duration equal to time of concentration. Since there is hardly any rainfall satisfying both these conditions, the estimation of runoff is only approximate by this method. So, obviously, it is very difficult to get a rainfall which is uniformly distributed over area of even say 100 hectares, forget about larger areas, or even few hectares, and also very difficult to get a rainfall where the intensity remains constant or uniform for the period, for certain period, which is in this case is defined as the time of concentration for the watershed. So, because it is very difficult to satisfy these conditions or to get in rain which is constant over the time of concentration or over the area. So, that is why these are the limitations of rational formula or rational method, and that is why this the estimation of runoff is only approximate by this method. However, for the design of relatively inexpensive structures where the consequences of failures are limited, this method is considered sufficiently accurate. But as I said that it is one of the very popular method for designing soil conservation structures, especially the temporary or structures having less life or low life, because in such cases even if the structure fails, the danger to life or danger to property on the downstream may not be significant. So, for in such cases this method gives a practical and simple value of peak runoff rate, and that is why this is quite commonly used. Now, in application of this particular method, it requires three prerequisites, that is, we require three important parameters. One is the time of concentration, because remember we say that time of concentration is important for finding out the duration of rainfall and the rainfall intensity, and that is what we say that rainfall intensity remains constant for a duration equal to time of concentration. So, I and Tc are linked, and of course, the runoff coefficient, if you remember we said that Q equals to CIA. So, this is the runoff coefficient we are talking about, this is here. So, this parameter also is very important, and we have to have an idea, fair idea of what is this parameter about. So, if we know all these things, the area of course is very easy to get. Of course, C will require the watershed characteristics considerations, and of course, intensity will require the time of concentration, because its duration is linked to the time of concentration. That is why this method is vital. Now, coming to time of concentration, it is the time required for the water to flow from the most remote point of the watershed with respect to flow time to the outlet. And this is, if you see, this is the, if you look at the picture here, this is the outlet of the watershed. So, if you locate the remotest point of the watershed, then whatever time the flow takes for traveling from this place to the outlet, of course, through the streams, that is referred to as time of concentration. There is a time required for water to flow from the most remote point to the watershed with respect to flow time to the outlet. Now, this is the furthest point of watershed we have located. Now, why this? What is the significance of this? The significance of this can be understood from this figure here, which simply says the runoff and rainfall rate. So, this is the rainfall rate it is telling, and of course, the runoff generation, runoff is here, and this is on this side, it is time. So, what is happening here, that it's if rainfall, because this assumption says that rainfall intensity is constant. So, if rainfall is occurring over a constant through constant intensity over a period of time, then obviously as we know that it will satisfy the abstractions, various kinds of abstractions, including the major abstraction infiltration, and then of course the runoff or overland flow will start taking place and the runoff will be generated. So, that means this is here. So, this is the gradually with time runoff increases, it keeps on increasing and then it peaks, and then it will continue with that peak rate as long as rainfall is continuous. Now, here at this point rainfall ends, and that is why you see that runoff is there is a recession in the runoff, that is it is decreasing up beyond that point. Now, the interesting thing is the peak value is obtained at duration equal to time of concentration. So, that is why, and that happens because when the water has reached from the farthest point to outlet, it is expected, and rainfall is continuing, then it is expected that entire watershed will be contributing to runoff, and that means the peak rate runoff will be when the water starts flowing even from the farthest point of the watershed. So, that is why when the rainfall duration is greater than Tc, then it is expected that peak value of runoff will be generated, and that is why this assumption that I should have a duration at least equal to time of concentration. Now, finding this type of data, that means in this entire exercise time of concentration is very important parameter, and there are several methods for determining time of concentration, and the most widely accepted method of computing Tc was developed by Kirpich in 1940. And as per this method, the time of concentration is given by equation number 10, which is Tc equals to 0.01947 L to the power 0.77 S to the power minus 385, where Tc is the time of concentration in minutes, because it is a kind of empirical relationship, that is why units are already fixed. So, time of concentration is minutes. L is the maximum length of flow in meters, and S is the slope of the watershed, and of course, this length is measured along the drainage line. So, of course, this is the, if this is the main drainage line, so on this L is measured, and S is the slope of the watershed, which will come by this relationship delta H by L, where delta is the elevation difference between the remotest point on the watershed and the outlet. So, if we know the elevation here and the elevation at the outlet, so the elevation difference between these 2 points is delta H, and if we know the flow path, we know the L, and that is why we can find out the slope of the watershed at delta H by L, which can be used here. So, S is here, L is here. Important point about this one is 0.01947 is that remember India's independence year 1947. So, it is very easy to remember for at least Indian students that it is it uses Kirpich formula uses a constant 0.01947. Of course, in some of the textbooks you will find that this value has been truncated to 0.0195. So, anyway, if you remember 1.1947 or 195, it does not matter, but this is one of the most popular ways of finding out the time of concentration for a watershed, because it just uses the watershed features for determining the time of concentration. Now, we come to rainfall intensity. Now, rainfall intensity corresponding to a duration Tc, just now we found out, and desired return period T or the probability of occurrence can be found from intensity duration frequency curve of the area. So, for this intensity duration frequency curve, we have already seen IDF curve of IDF analysis we have already discussed. So, obviously, we know that the average intensity for any known duration can be read for different recurrence intervals from this graph, and usually this relationship is of this form: I equals to KTX by Tc plus a to the power m, where k, x, a and m are constants. But you remember, while discussing the IDF curve, I gave it example of a relationship that has been developed by Kothari and Gerde in 1992, which slightly differs from this relationship, but of course, most of the parameters are same. There is one additional parameter there into R224 was used in that particular method. Then comes the runoff coefficient C, and this runoff coefficient represents the integrated effect of catchment characteristics as a function of surface condition and slope. And runoff coefficient may be expressed as ratio of runoff and rainfall, that is C equals to R by P. That means it is simply, if we know rainfall and we know runoff and we know precipitation, then it basically tells us what percentage of rainfall gets converted into runoff in simpler terms. So, this can be of course, there are standard tables from which we can determine this value of this value of C, but this is what the relationship. So, TC we have discussed, I we can determine, C we can determine, and thus we can use the value. This is the recommended value of runoff coefficient C for different types of drainage area. Like here we have urban area, we have agricultural area. Like urban area we have lawns, residential area, industrial area and streets, and agriculture area we have flat lands and hilly lands, and as you can see the value ranges. So, for example, a flat sandy loam cultivated, the value is 0.2, when sandy loam cultivated under hilly regions the value is 0.4, and you remember that we said that C basically shows what percentage of rainfall gets converted into runoff. So, obviously, it clearly shows that if it is a hilly terrain, similar land and cultivation soil and cultivation conditions, then from a hilly agricultural area runoff will be twice that from a flat agricultural area. So, this is what we get to see here. Now, we have to consider yet another thing, that is runoff coefficient for non-homogeneous areas. If you remember, in the previous table the value is given for a specific area, but that simply means that initially it was assumed that runoff watershed has homogeneous land use, soil and slopes, and everything is uniform. But practically, because it is not possible, typically watersheds are non-homogeneous, characterized by highly dispersed areas having different runoff coefficients. In such cases, we have to use weighted runoff coefficient, that is using this relationship Cj, Aj, Aj, where Cj is the runoff coefficient of area J, N is the number of distinct land covers within the watershed, and Aj is the area of the land cover, Cw is the weighted. So, for example, if you have a watershed where you can distinctly see that there are 3 different uses or land characteristics or whatever features, that is based on, because it takes into account land slope and land use and soil and land slope. So, if these 3 different features are there, that means in that case our N value becomes 3, and that means we have to find out the area under each of these, that is area Aj, which we are calling, and the corresponding Cj. So, if I know Aj, Cj of all 3, so the sum of Aj, Cj will give me numerator, and total area is of course the denominator. So, I can get the weighted runoff coefficient for a non-homogeneous area. So, let us take an example here, and an agricultural field has a runoff coefficient of 0.25 and an area of 0.75 square kilometers. The slope of the catchment is 0.45% and the maximum length of travel is 1.2 kilometers. The maximum depth of runoff rainfall with 25-year return period is as follows. So, here we have been provided table where we have for different durations, we have given the depth of rainfall in millimeters. So, duration in minutes and depth are in millimeters, and drop spillway has to be designed for area return period of 25 years, and of course, we have to determine the peak flow rate for designing this structure. So, of course, we can use the rational method in this case. The values that are given or known are the maximum length of travel L equals to 1.2 kilometers. We are converting that into 1200 meters. The slope of catchment is given 0.45. We may use Kirpich formula to determine the time of concentration, and that formula is 0.01947 L to the power 0.77 S to the power minus 385. So, value of L and value of S is known to us. By putting these values here, we get Tc equals to 36.63 minutes. Now, we have been provided table having different durations and depth of rainfall. So, now we have to find out of course, the intensity of rainfall for a duration equal to time of concentration. That means, we have to first find out the depth of rainfall for 36.63 minutes, and that we have to convert into intensity for being able to use that into rational method. So, obviously, then for 36.63 minutes we need to interpolate. So, obviously, the value will come in between here, because this is 30 minutes, this is 40 minutes. So, 36.63 will fall in between these two. So, that is why we are interpolating 62.55 times 6.63, that is 36.63, that means from here it is 6.63 divided by 20, and of course, for 30 it is 55. So, using this, the maximum depth of rainfall for 36.63 minutes of duration, we get 59.64 millimeters from this table, and because we know the duration, we know the depth. So, obviously, we can find out the rainfall intensity, which comes out to be 97.69 millimeter per hour, or 2.71 into 10 to the minus 5 meter per second. That is the unit we require this fee to be able to use. And that simply means that rainfall intensity value we have already obtained. Runoff coefficient is already given as 0.25. Area of the watershed is 0.75 square kilometers. So, obviously, we can convert that into square meter. It will come out to be 0.75 into 10 to the power 6 square meters. So, now we need all the requisite parameters are available with us. So, we can use the rational formula QP equals to CIA, and so CIA, all these values we can use, and we get a value of 5.08 cubic meter per second. So, using the rational formula, the peak flow rate for designing the drop spillover in the area, that is for return period of 25 years, comes out to be 5.08 cubic meter per second, or 5.08 cumex. So, this is how we can estimate the values here. Now, we take another example, and that is a 100 hectare watershed received rainfall at a rate of 50 millimeter per hour for 2 hours. If the runoff generated by the storm was at a rate of 1 cubic meter per second for 10 hours, then find the runoff coefficient for the watershed, and this question is taken from GATE 2013 examination. So, now of course, if we decide that we want to use rational method, so that means we need these Q equals to CIA, but in this case the 100 hectare watershed received an area of 100 millimeter. So, we have been already given, of course, we have to get the runoff coefficient. So, basically we do not have to use this formula, but instead we will use C equals to R by P. So, we do not need to go for rational formula in this particular problem. It is a simple problem where we have to simply, knowing runoff, knowing precipitation or rainfall, we can determine the value of C. So, that is that simple a problem. So, intensity of rainfall is given as 50 millimeter per hour, and duration of rainfall is given as 2 hours. So, obviously, we need to convert that. So, total depth of rainfall is P, that is I times D, that is intensity is given as 50 millimeters per hour, and duration is 2 hours. So, 50 times 2, that will give us a value into millimeters, and thus the total depth of rainfall we get is 100 millimeters. So, that means the denominator we have obtained is 100 millimeters. Now comes the numerator R, and the runoff rate is given as 1 cubic meter per second. So, runoff rate is given as 1 cubic meter per second. The duration is given as 10 hours, and duration is given as 10 hours, and total 1 cubic meter per second. Watershed area is given 100 hectares, and duration is given at 10 hours. So, 10 hours we convert into seconds, comes out to be 36,000 seconds, and watershed area is given in 100 hectares, that comes out to be 10 to the power 6 square meters. So, that simply means what? The total depth of runoff, because here you remember we have been given in cubic meter per second. So, if we multiply the runoff volume, actually we will get runoff volume equals to rainfall runoff rate QP times duration, that is QP is given as 1 cubic meter per second and into 3600 seconds. So, that simply means we get a value of 3600 cubic meters. That is what we get the runoff volume in depth units. So, it's in millimeters, or sorry, it's in cubic meter. It's not in depth units, it's a volume. And what we require, because our rainfall is in depth units, so of course we require runoff also in depth units. So, total depth of runoff we can divide this 3600 by 100 10 to the power 6. So, we will get 36,000 divided by 10 to the power 6. So, we get 0.06 meters or 36 millimeters, and once that means the numerator value is 36 millimeters. So, total runoff coefficient for the watershed is R by P, that is 36 by 100 or 0.36. Instead of doing all these things, what is done here is that simply QP and T is multiplied straight away, 1 into 36,000 which is here, and this is divided by area, which is 10 to the power 6. So, that is why we are getting this total depth of runoff. You can do it in 2 steps also, that you can first calculate the runoff volume and then divide by the area to get the total depth of runoff depth in millimeters, and so we can calculate the value of C here, which comes out to be 0.66. So, that simply means that 36% of rainfall gets converted into runoff in this particular problem. Now, we will take up another example. Calculate the design peak discharge expected to occur once in 25 years at a site for constructing a drop structure to handle the runoff from a watershed comprising of 20 hectares of cultivated land C equals to 0.5, 15 hectares of hilly forest land C equal to 0.3 and 8 hectares of rolling grassland C equals to 0.35. The maximum length of flow is 2 kilometers and the total fall along the path is 20 meters. The maximum rainfall recorded for various duration is 25 years and they are given as below. And so, duration each year, depth of rainfall here, that is for 25 years return period, and this question came in GATE 1991. So, obviously, because in this case we have been given a watershed with multiple land uses. So, obviously, we have to get the weighted runoff coefficient, and we have been given cultivated area over 20 hectares, hilly forest area over 15 hectares and rolling grassland with 8 hectares, and of course, the runoff coefficient values are also given. So, knowing the runoff coefficient values and area, we know that Cj, Aj, sum of that will give us the numerator and sum of the area will give us the denominator. So, by putting these values here, we can calculate the runoff coefficient is 0.4. The maximum flow length is given as 2 kilometers or 2000 meters. The elevation difference between the remotest point on the watershed and the outlet delta H is given as 20 meters. So, watershed slope we earlier saw that is delta H by L, and so 20 by 2000 we get a value of 0.01. So, we can calculate the watershed time of concentration of watershed using Kirpich formula, which is 0.01947 L to the power 0.77 S to the power minus 385. The value of L already we have calculated is 2000 meters and slope we have calculated is 0.01. So, putting these two values, we can calculate the value of TC, which will come out to be 39.92 minutes. That is what we are getting here. And time of concentration thus comes out to be 39.92 minutes. Now, because we have been given for different durations the depth of rainfall, so as we did in earlier example, we have to first get the depth of rainfall corresponding to this time of concentration and then get the intensity. So, obviously 39.92, so very close to 40, but we have to interpolate between these 2 points. So, obviously 90 minus 50 times 19.92 divided by 20, because this difference is 20 and this is starting from 20 here, this is 19.92. So, that is why 19.92 by 20 times of the difference between these two we are taking, and of course, the base value of 50 we are taking. So, total runoff depth, rainfall depth comes out to be 89.84 millimeters in this 39.92 minutes, and we require the average intensity. So, obviously, we have to, knowing the depth and the duration, we can convert that into intensity, and we get 135.03 millimeter per hour or 3.75 into 10 power minus 5 meters per second. And the total area, of course, we already know, we have used in previous while calculating the coefficient, is 43 hectares or 43 into 10 to the power 4 square meters. 1 hectare is 10 to the power 4 square meters, and that is why we are multiplying that. So, obviously, we now know C already we have calculated, I we know, A we know. So, by putting the value in this equation, QP equals to CIA, that is C equals to 0.4, I equals to 3.75 into 10 to the power minus 5, and A is 43 into 10 to the power 4. So, by putting all these values, we get a value of QP equals to 6.45 cubic meter per second. That simply means that the design peak runoff rate for designing the drop structure in this watershed comes out to be 6.45 cubic meter per second. So, that is why that is how we saw that the one of the most popular method, rational method of peak runoff rate determination, how it can be used under different conditions and a given data. With the given data, we can use that, and just to recall, important thing is that we have to determine the time of concentration, for which we need the length and elevation characteristics of the watershed, and of course, we know the rain for that duration we have to find out the rainfall intensity for the required return period, for which we may have to use the intensity duration frequency curve, and of course, for finding out the C, that is runoff coefficient, we have to use the tables provided already available for different given conditions. So, after knowing CIA, we can use this relationship to get the peak runoff rate. So, with this we come to end of this lecture. Thank you very much for please give your feedback and also raise your doubts or questions in the forum, which will be happy to answer. Thank you very much.